Good to go. All right, Ms. Stone here. This is grade 12 University Prep Physics, and we're looking at, I don't know, something that's pretty wicked awesome. And it's particularly awesome, I think, because we get to actually show this, do a laboratory. Not very much cool physics can we do a laboratory on, and this we can. It's not too bad. But what this was, early, like in this time, right, 1799, early in this time, people didn't understand light very well, obviously. And there was actually two dueling theories, and you should, this is one of the research assignments I get you to do, is on Newton's theory that light traveled as tiny particles. He called them corpuscles, so that's why it's called corpuscular theory. And then there was a guy, Huygens, who his theory was like that light traveled in waves. And so those were the theories of the time. And what Thomas Young did is he actually did an experiment trying to make something like, like this, not necessarily the mathematical part of that, but just the, well, he used the same math actually, but, he thought if he created two in-source waves of light that would interfere with each other, well, if they were waves, would they interfere, and what would that look like, right? That's really what he was trying to do. And he did that to be sure that they were, in phase. He did what's called the double slit experiment. And yeah, well, you'll do your own double slit. You'll see exactly what I mean. I'll show you in a sec. But pretty much what he found, though, was that, light did create an interference pattern. Like when you had two sources of light traveling in phase and they were allowed to interfere with each other, they did, and it was very predictable. And so he basically took then all the equations I showed you earlier, but he modified them so that we could calculate like the wavelength of light using a pattern. And I'll show you that very soon. So it was definitely true that light has properties of particles. One little example of one, and I would just do the research to get the rest, but one example of one is that light travels in straight lines just like you expect a particle to do. If it bumps into something, it reflects according, just like you expect a particle to, right? However, there's also wave-like properties, and that's sort of the dual wave-particle duality of light. It's not very well, it's accepted, but maybe not truly understood. How is that possible? Anyway, this is a kind of a neat little video that goes on to that, a larger scale, way cool, that not only does light have properties of waves and particles, but so does matter, so does stuff, stuff like us. Let's just watch this video.
And here we are, the granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So when we throw things, that is matter, through two slits, we get this. Two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum.
Quantum means it goes small, very small.
An electron is a tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought maybe those little balls are bouncing off each other and creating that pattern. So they decide to shoot electrons through one at a time. There is no way they can interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits, and it goes through neither. And it goes through just one, and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. The electron decided to act differently, as though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never-world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this? The observer collapsed the wave function simply by observing.
All right, so that's crazy. It's crazy, and quantum physics is, I wish I understood it well enough to teach it, because it's crazy. I mean, Niels Bohr said about quantum physics, which is the physics of the tiny, that if you think you understand it, then you have no clue. So I'm sort of proud of saying I don't understand it. It must mean I have a small clue. But so that's we don't need to explain that with very much precision, but it is a cool idea, and it does give you a visual of what I meant by the double slit experiment. You will do the double slit experiment yourself, so you'll have a great visual on it when you do it yourself. But that's what it looks like. You got a little plate with the two slits in it. You shine light through it, and what you'll see is an interference pattern. You're going to do it on the blind in my room, and if you notice by where I sit, the blind has little signatures and has marks on it. That's the results of the Thomas Young experiment. So you guys are going to sign that. So when you do your Thomas Young, you're going to sign it. I'll get to keep your name on my board forever. Anyway, but that's what the experiment looks like, and the fact that it applies to matter is way cool, but not necessarily something we need to concern ourselves with in this unit. That's just what the light experiment is, what we need to concern ourselves with. So, here's a better picture then. Source of light, two slits, creating an interference pattern. This is the interference pattern that you see. So again, when you do this experiment, you're going to stand near the smartboard, shining light. Someone's going with a nice steady hand is going to be holding a slit plate. Actually, the slit plate's pretty close. We do it pretty close. And then someone else is going to be by here by the blind, and you're going to measure sort of the distances between the bright spots, which is really the delta x in this equation, because this is where all that path length difference, those equations break down nicely into this little equation that we can use for light, to find the wavelength of light. So imagine when you shone your light, for example, you didn't know the color. And you could get the, by, you could calculate, you could, by the experiment, you'd find the wavelength, and then you could look up the color. Obviously, you're going to see the color, but what that allows you to do, though, is to calculate your percent error. You know, because I find that kids often either get it really close, or it's like orders of magnitude off. Like it's one or the other, bang on, or it's never off by like 20%. You know what I mean? It's always off by either 1 or 2% or 2,000% or something. But anyway, you'll do it, and hopefully you'll get close. So these are the things you'll measure when you do the experiment, right? Delta X then is really this distance right here. I'm sort of, you watch my mouse right now. What you do is you take a whole bunch and you divide. You'll see. Here we go. So this is actually, when you do the experiment, this is exactly what you see on the wall, on the screen. You see this exactly. And what you do is you sort of pick a spot and you count the number of spaces in between it. So say we have a 10 centimeter spot, then you calculate the number of sort of, like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sort of 12 pieces there, and that's the delta X. Okay, and that's how you find delta X. And yeah, these dark spots are the where they cancel each other out, the nodal lines. So you kind of measure how many sort of adjacent nodal lines there are. Constructive interference here, nodal line there. So say here's an example. When you do the lab, this is exactly the calculation that'll go with it then. So you have a slit distance of 0.1 millimeters. That, when you use my slit plate, there's a little sheet of paper that tells you the differences, the distances, sorry. And you create an interference pattern on a screen. The 2.5 meters away, that's the L in the equation. And the distance between the first and fifth dark line is 4.5 centimeters. So just what I mean, like would be, say, one, like, and I think when I said first and fourth, it might have been, there's the brightest one. So say from here, so it'd be first and fifth would be, there's the first, 2, 3, 4, 5, right? So when you measure the number of spaces between there, though, in a space like that, it works out to there's 4 spaces in between. And you calculate your delta X. And then we're going to find the wavelength by applying Young's equation there, solving for wavelength. And you get, this is, your number should always be something times 10 to the negative 7 meters, right? Then if you multiplied it by 10 to the 9, you'd get 500 nanometers. And that would be a typical wavelength for, did I say what color it was? Because that sounds like yellow, not red, maybe yellow. No, it doesn't tell us the color, but we can look up the wavelengths of different colors. We'll do that soon anyway. But yeah, usually the numbers are in here, 400 to 750. So 750 is red, 400 is like blue. So you know it's going to be in there somewhere. Okay. Oh, here we go. So what did we get on that one? That one was what? 500? So 500 would be green. So that would have been green light. And so, by the way, when you do Young's, you're going to do a green light and a red light. Okay, just another little thing about color. This, by the way, if I wanted you to use it on the test, I'd probably give you the information. Okay, sometimes you get a color, so, like you should have this, and as you do in your notes, because sometimes you get a question. I think one of your assignment questions is, what color light would this have been? And they'll give you a Young's experiment. You calculate the wavelength, compare it to the table to get the color. But anyway, this one's actually simpler. This one's just saying wavelength of red light's this, determine its frequency. So actually this is really simple because this is just going back to universal wave equation. I'm not even using Young's. Okay, so you use V as the speed of light, use the wavelength of red light, and there you go. And it should be, that's a huge number, and it should be, because it's just, remember, that's how many times per second the wavelength moves. Like it goes back and forth, one full wave. And it's going to be super fast. It's light. Okay, so say you're colorblind, you're performing a Young's experiment, you got your D, got your L. It is found that the distance from the fifth bright line to the right of the center is 35 millimeters. So what color of light is shining through? So usually when it says that, from the fifth to the right of the center, so the fifth to the first sort of thing, that means there's 4 spaces. Okay, so if it says that, Usually you know it's going to be 4 you're dividing by to get your delta x. If you're not sure, try to sketch it out and draw it. Anyways, you're just looking for lambda. You know, pretty easy. You go through, you get your lambda, then you can compare it to the table to find out its yellow light. And what I mean by table is this one, of course. 583 fits in this range. Okay, that's it for this video. We have 2 more videos in this unit still.